In this video, we present 3 experiments of our paper. The first experiment was conducted in gazebo simulation environment. In this experiment, the aerial manipulator was teleoperated to fly through 2 windows. The purpose of this experiment is to demonstrate that our approach enables the aerial manipulator avoid obstacles autonomously while following the human operator's intention. When passing through the first window by PV control, the velocity of the aerial manipulator deviates from the velocity reference, since the aerial manipulator must avoid obstacle collision. When passing through the second window, the control mode is switched from PV control to PP control. While the delta manipulator remains almost static relative to the base in PV control, the aerial manipulator can automatically shrink the delta manipulator to pass through the second window. After the aerial manipulator passed through the window, it expanded the delta manipulator back to its original shape. Therefore, our teleoperation approach fully utilizes the unique features of aerial manipulators to adapt to different scenarios. Next, we show a comprehensive flight experiment where the proposed control approach was applied to an aerial pick-and-place task in an obstacle-rich environment. This is the aerial manipulator platform used in the experiment. To achieve the task, the aerial manipulator should take off from point A, pass point B, reach point C, and pick up a board, and then place the board at point D. The PV control mode was used to teleoperate the aerial manipulator to move efficiently from point A to point B. During this procedure, the aerial manipulator avoided the pillar obstacle autonomously. The PP control mode was used to teleoperate the aerial manipulator to move from point B to point C. During this procedure, the aerial manipulator retracted its delta manipulator to avoid the window barrier autonomously. To pick up the board at point C, the human operator used PM control, so that the end effector can be in contact with the environment safely. In this experiment, the human operator tried to pick the board twice. The first try failed because the cups did not suck the board tightly. Even if the first try failed, the aerial manipulator still flew safely. The purpose of the third experiment is to demonstrate the safety and robustness of our approach under unfriendly, or even dangerous human operation. Specifically, the human operator deliberately guided the aerial manipulator to crash on the floor and, in the meantime, switched control modes frequently. This kind of operation is dangerous, but our approach can still ensure safe and smooth flight in this case. As can be seen from the video, the velocity or position of the aerial manipulator does not converge to the velocity or position reference due to the existence of the floor. Furthermore, in PV and PP control, the aerial manipulator always kept a distance from the floor to ensure the safety of flight. In PM control, the end effector of the aerial manipulator was in contact with the floor safely. Moreover, the aerial manipulator flew safely and smoothly all the time, even for the moments when the control mode was switched.